Hello everyone and welcome back. Have you ever wondered whether modeling bolts as solid elements is really worth the extra computational cost, or if beam elements can deliver reliable engineering results? In this video, we are going to compare both approaches using the exact same model, the same geometry, the same material properties, and the same boundary conditions. We will compare the axial force and shear force in M8 bolts and discuss when each modeling technique is the better choice. So let's get started. For this comparison, I created two finite element models that are identical in every aspect except for one thing, the bolt representation. So in model 1, the M8 bolts are modeled as 3D solid elements, and in model 2, the same M8 bolts are modeled as beam elements. Everything else remains unchanged. So the geometry the same, we have two rounded plates, 5 mm thick each one of them. The material property used is the same, we use like here structural steel with a modulus of 210 gigapascal. The contact definitions, we have like a frictional contact between each one of these plates, and under the head like bolt, between the head of the bolt and the top plate, we have like a frictional contact with a frictional coefficient of 0.12. The boundary conditions and applied loads also, they are the same. We have like a fixed support on the bottom face of the bottom plate, and on the top face of the top plate we have like an upward force of 20 kilonewton with like a small force in the x direction around like 2.5 kilonewton acting on both models. So this allows us to isolate the effect of the bolt modeling method and make a fair comparison. Let's begin by looking at the axial forces in the bolts. For that, as we learned before in the previous videos, in order to get the external axial forces acting on the bolts, we need to initiate like simulation without bolt pretension. I did prepare that for you, and actually I got the following. As you can see to the left, we have the model when we have the bolts as a beam, and to the right when we have the bolt as a solid elements. To the left, you can see like from the axial force acting on each one of these M8 bolts as follows. And when we have the bolts as a solid, we can see the axial force acting by looking into the reaction force from the contacts we have between the bolt and the top plate. And we can just like look into the force reaction in y direction, and that like is actually the external axial force acting on this bolt, and you can see the other force reaction, so you can get the other like external force acting on the other bolts. I already like took these like values and put them like in a table in an Excel, so we can like compare them like later on with the same results, but when we have a bolt as a solid and as a beam for both axial and shear forces. Before that, let's compare the shear forces. And to get the shear forces, we have to go back to the models with bolt pretension. And from there, we can get like directly with the beam model, the shear forces acting on each one of these bolts. And on the other hand, from the force reaction, all what we have to do actually is to calculate the square root of the value in x direction, like square plus the one in the z direction square, so we can get the final like magnitude in shear like a plane that's like xz. And we have to do this for each one of these bolts, so we can get the final like results for the shear force acting on each bolt. So let's go and see the results together. As you can see now in these tables, I already like input all these values, and what we have to look into it actually these two tables. The first table is like relevant when the bolt as a solid modeled, and the second table is when the bolt as a beam modeled. Now, as you can see, when we are looking into the axial forces between the two models techniques, both models like predict like a very similar load distribution. However, there are like noticeable differences in the magnitude of the forces due to the different assumptions behind each modeling technique. For the shear forces, again, the overall trend is very similar, but the values are not exactly identical. This is like expected because the two approaches represent the bolt stiffness and load transfer differently. The important question is not whether the numbers are identical, but whether the differences are significant enough to justify the additional computational effort. So from this comparison, we can like clearly see that the both modeling techniques have their own strengths and limitation. Using a beam model actually offers several important advantages. So the model is much faster to build, meshing is simpler and more robust, the solution time is significantly lower, and it requires much less computational memory. For large industrial simulations, these advantages can make a huge difference. But when, on the other hand, like when we have modeling the bolt as a solid elements, provides like a more detailed representation, as you can see on this model, and actually provide us like a more detailed representation of the actual physical behavior. So because of the bolt geometry is explicitly like modeled, this approach generally produces results that are closer to reality, especially when local stress distribution, contact behavior, or detailed bolt mechanics are important. So the trade-off, however, is the much higher computational cost, longer solution times, and increased modeling complexity. So which approach should you choose? For engineering models like the one demonstrated in this video, I believe that modeling bolts as a beam elements is the more practical and efficient solution. It provides like reliable engineering results while dramatically reducing modeling effort and computational cost. In many engineering applications, this approach actually is this approach is slightly like conservative, and being conservative is often like a good thing when making design decision. When we are look like again to the result, as you can see on the axial forces, we have like over the all four M8 bolts like with the bolt when modeled as a beam like slightly higher like axial force as we got like from the solid model, which is like slightly like conservative, but it's like at the end like a good thing. So if your objective is to study the detailed behavior of an individual bolt or investigate like local stresses with the highest possible accuracy, then the solid bolt modeling becomes the preferred option. Ultimately, the right choice depends on the purpose of your analysis. So before we finish, here is something like interesting. In this study, the upper plate actually that we used like was relatively like thick. But what happens if we repeat the exact same comparison using a thin plate instead? Will the beam model still agree with a solid model, or will the differences become much larger? The answer is actually quite surprising, and it leads to an important engineering conclusion that could change how you decide to model bolted joints in future simulations. We will investigate that in the next video. I hope this comparison helped you better understand the advantages and limitation of modeling bolts as a beam elements versus solid elements in finite element analysis. So if you found this video helpful, don't forget to like the video, subscribe to the channel, and let me know in the comments which bolt modeling technique you typically use in your simulation. I will see you in the next video.